Section 10.1 Correlation. Suppose I want to determine whether a relationship exists between the number of hours of sleeping for a student and the GPA at the college of the student. How could you determine if any relationship exists? Definition. Correlation exists between two variables when the values of one variable and somehow associate with the values of the other variable. So for these sessions, we will have two variables and we want to know if these two variables are associated with each other. And we call this as a correlation. A linear correlation exists between two variables when there is a correlation and the plot points of the pair data result in a pattern that can be approximated by a straight line. One type of correlation is called linear correlation. And if you want to know if these two variables, that is a linear correlation, we will construct a scatter plot. And if you could see all the points is going to be around on the straight line, then we say there is a linear correlation. For these sessions, we'll be focusing on the linear correlation. Remember on the session 2.3, you guys learned how to graph the ordered pairs, and that is called scatterplot. Scatterplot can be used to determine whether a linear correlation exists between two variables. For example, for the first scatterplot, you could see all those points is going to be going on like this direction. And you could draw the straight line on it. And all the points is going to be around the straight line. And we call that is a linear correlation. You're going to see this means like negative. This means when x is increasing, the y is going to be decreasing. Or you could think about it. The slope of this linear equation is going to be negative. So we know this is a negative linear correlation. For the second one, all the points is going to be going on this direction. We can draw the straight line on it. All the points is going to be around the straight line. So we say there is a linear correlation. And since the slope is going to be positive, so we call this as a positive linear correlation. And number 3 here, you could see we don't have any pattern. And also, I can't draw a straight line on it. So we're going to say this is a no correlation. Number 4, for this picture, you could see we do have some pattern on it, right? It looks like the parabola. However, we can't draw the straight line on it, so we're going to say this is a nonlinear correlation. I want you guys take a look with the picture 3 and the picture 4 here. For the picture 3, since we don't have any patterns, so we could say this is a no correlation. But for the last picture here, you do see some kind of a pattern here, but this is just not the straight line pattern. So when we draw the conclusion, we only can say this is a non-linear correlation. Keep in mind that we do have a different types of correlation. We only study for the linear correlation for this session. So if you see there's some other patterns, you only can say non-linear correlation. Interpreting correlation using a scatter plot can be subjective. You could see all the points is really close to the straight line. But sometimes all the points may not be really close to on your straight line. And if you want to know if there is a linear correlation, we're gonna find out the correlation coefficient R. The correlation coefficient R is measure the strength of a linear correlation. For example, for the first picture here, you could see I could draw the straight line here. And all the points is going to be on my straight line. So if you guys use the data to find the R, you could find the R equal to 1. And this is called perfect positive correlation. And again, this is a positive because the slope is going to be positive. Or you could look at the value here, this is going to be positive 1. Okay, this one. I still can draw the straight line in here, and the points is going to be close to my straight line. When you guys use the data to find the R, you're going to find it out that's equal to 0.81. And we say this is a strong positive correlation. This one, I still can draw the straight line here. However, all the point is not really close to my straight line. So when you guys use the data to find the R, you will find the 0.45. And we consider this as a weak positive correlation. Same idea for this picture. All the points is going to be on my straight line. Slope is going to be negative. So I know my R is going to be equal to -1. Here, strong negative correlation because all the points is going to be close to my straight line and the slope is going to be negative. And this one, I didn't see any pattern here. If I use the data to find the R, you could see the R is going to be equal to 0.04. Since the R is really close to 0 and we don't see any patterns from here, so we could draw the conclusion say there's no correlation. It is important to remember that if R close to 0, it does not mean that there's a no relation between X and Y. You only can say there is a no linear relation. Remember there is a different types of correlation. Since we only studied the linear correlation, so even though you find your R close to 0, you have to look at the scatter plot to see if they have any other pattern. If they don't, then you could say no correlation. If you see the picture like here, you may find your R close to 0, but you could see there's other patterns in here. So you only can say nonlinear correlation. Properties of the linear correlation coefficient. Assume R is the linear correlation coefficient for the correlation between two numerical variables. The values of R are between -1 and 1. So your R is always in between -1 to 1. If R is positive, then the variables are positively correlated. So if your R is equal to the positive, you're gonna know the slope is become the positive and it's gonna be going on this direction. Okay, it's gonna be increasing. If your R is negative, then the variables are negatively correlated. So you're gonna see if you find your R is between -1 to 0 here, the R is a negative. And your slope is gonna be going like this way. That will be the decreasing. If R equal to 0, there is no linear correlation. Okay, R equal to 0 or really close to 0, we're gonna say there's no linear correlation. Okay, more properties for your R. The larger the value of R, the stronger the linear correlation will be. So I know the R is always in between -1 to 1 here. If your R equal to 1, then the points lie exactly on the line and the correlation is positive. We talked about this one already, right? All the points is going to be on my straight line. So my R is going to be equal to 1. And we call this is perfect positive linear correlation. And if R equal to -1, all the points is going to be lying on my straight line and the correlation is negative. So we call this as a perfect negative linear correlation. If your R is lying between from 0.5 to 1, we call this as a strong positive linear correlation. Lying in between -0.5 to -1, we call this a strong negative linear correlation. If your R is lying in between -0.5 to +0.5, we're gonna say this is a weak linear correlation. If R equal to 0 means there's a no linear correlation. Okay, more properties. If all values of either variable are converted to a different scale, the value of R does not change. Remember when we construct the scatter plot with two variables, if you guys change the scale, it doesn't affect for your R here. The value of R is not affected by the choice of X and Y. Interchange of all X and Y values and the value of R will not be changed. So this is talking about you have these two variables. It doesn't matter which one is going to be your X, which one is going to be your Y. You could interchange of it and your R will not change. R is very sensitive to outliers, which can dramatically affect the value of R. Remember what is the outliers? After you guys construct the scatter plot, if you see the points is far away from the majority, we consider that will be the outliers. And if you see the scatter plot that's an outlier, you need to remove of it. Otherwise, it's going to be dramatically affect your value of R. Okay, requirements. First one, sample of paired data is a simple random sample. Visual examination of the scatter plot must confirm that the points approximate a strychnine pattern. So before you guys calculate the R, you need to construct a scatter plot and make sure all the points is going to be close to a strychnine. Last one, outliers must be removed if they are known to be errors. The effects of any other outlier should be considered by calculating R with and without the outliers included. So after you know if that's an outliers, you have to double check your data. Did you guys make any mistake when you collect the data? If you know that's the error, you're going to remove it. If not, you may remove it and analyze those outliers. And after that, you're going to calculate your R. Okay, notation. So N represent the number of pairs of a sample data. So you're going to count how many order pairs do you have. This is called the summation notation. Means you want to add it up all the data. Summation of X. So you want to add up all the values of X. Summation X squared. This is talking about you're going to take square first and then add it all up. And this one, you want to add up all the X first. At the end, you want to take the square. Summation X of Y. So you want to do X times Y first and then you want to add it up. Summation X times summation Y. This is talking about you want to add up all of your X, add up all of your Y, and then you're going to multiply it. I will show you guys an example for the next slide and let you guys know what's the difference between these two and what's the difference between these two. Okay, two more notation. This one, the R. R is called linear correlation coefficient and this is specific for the sample. Okay, just like you have the sample mean or population mean. And the R here, this is called the sample linear correlation coefficient. And then this is the rho, okay? Hey, look at this notation. This is not the P, okay? This is the rho. We call this as a population linear correlation coefficient. Okay, look at this example. So how many order pairs do I have? I have 1, 2, 3, right? So my N should be equal to 3 here. And then I want you guys try to do it by yourself. Find it out what is the summation X squared, summation X, and then square, and then summation XY, and then summation X times summation Y. Just show me all your work, okay? You don't have to get the final answer. For example, summation of X, I want to add up all the X in here. So 1 plus 2 plus 3. Okay, just show me all your work. Summation x squared. So you want to take the square first and add it up together. Okay, so 1 squared plus 2 squared plus 3 squared. Summation x and then take square. So this means you want to add up all the x values and then take the square of the total. Make sure you guys don't mess up these two. Okay, one is without the parenthesis, one is with the parenthesis. Okay, summation x of y. So this one you want to multiply x and y first and then add it up together. So you will have 1 times 4 plus 2 times 5 plus 3 times 6. Last one. You're gonna add up all the values of x, add up all the values of y, and then you're gonna multiply together. Okay, again, don't mess up these two also. Why do we need to know all this notation? Because we want to know how to find my R. And finding the linear correlation coefficient R, we do have a two method. First one will be using the formula. I just explained to you guys how to find the summation xy, summation x, and summation y. But actually, for like those numbers, summation x, summation y, summation x squared, we'll use the calculator to take care of it. So this is the instruction, how you guys use your calculator to find the summation for this formula. This is the first method to find your R. Second one, strictly using your calculator. And you guys need to know both of the method. On the homework and also the final, I may ask you guys use the formula to find the R. Or I may ask you guys just use your calculator to find the R. Okay, common errors involving correlation. Common error is to assume that correlations implies causality. We talked about this one from the chapter 1, right? You don't assume that correlation implies causality. For example, there is a correlation between the number of the cigarette smoke and the pulse rate. So I know these two variables, cigarette smoke and the pulse rate, they are associated with each other. But I can't draw the conclusion to say that the number of the cigarette smoke causes a person's pulse rate to change. I only can prove that there is association between these two variables, but I can't say that's a one variable to cause another variables to happen. So we say correlation does not imply causality. However, you can say causation implies correlation. Okay, another common errors. If there is no linear correlation, there may be some other correlation that is not linear. So even though you find your R equal to 0 or close to 0, you only draw the conclusion saying that there's a non-linear correlation. Unless you look at the scatter plot, make sure they don't have other types of the pattern. Okay, let's try the first example. Number 1, a small company has 5 employees. The following table presents the number of years each has been employed and the hourly wage in dollars. So we have the X and the Y variable. A. Using the calculator to find the correlation coefficient R. 1 to 3 decimal space. So let's use the calculator. We're gonna go to the stat, go to number 1 added. So if you have a data, remember how to clear it. Highlight the L2, click clear, click enter. Do the same thing on the L1. Highlight the L1, click clear, enter. So for my L1, I'm gonna plug in my X. L2, I'm gonna plug in my Y. Plug in X on your L1, Y on your L2. And then click on the stat, go to the test, go up, you're gonna see the linear regression t-test. Enter. So my X is gonna be on my L1, Y is gonna be on my L2. Frequency, keep it as a 1. Here, I just put it not equal to 0. Go to the calculate. Enter. So here, go down, you're gonna see R equal to 0.906. So you can see your R equal to 0.906. So write it down here. Okay, B, construct a scatter plot. So go back to your calculator. After we have the R, we're gonna keep going. So we're gonna click on second, Y equal to. Make sure you turn it off from number 2, 3, 4. Now we want to turn on the number 1. So you're gonna press enter. Okay, you're gonna see my port 1 is off, so I'm gonna turn it on, enter. Go down, use the arrow button left or right. So we're gonna go to my number 1 here. And then my X is gonna be on L1, Y is gonna be on L2. For the mark here, doesn't matter which one you use. It just shows your order pairs. So I will just use like this guy, enter. Okay, now click on the zoom. Zoom is gonna be on the top in the middle button. Click on the zoom. Look at the zoom stat, okay? Number 9 zoom stat, click on 9. You're gonna see this is gonna be my scatter plot. I want you guys copy this picture, okay? That will be my scatter plot. C, using the formula to find the correlation coefficient between the years of service and hourly wage. So I want to find the R again, but this time I want you guys to use the formula. So calculator. I already have the data on my L1 and L2, right? Double check, stat, number 1 added. I have my X on my L1, Y on my L2. Now I want to find out the summation X and summation Y. So I'm gonna click on the stat, go to the cal, click on number 2, 2 variable statistic. So my X is gonna be on L1, Y is gonna be on L2. Go to calculate. So you're gonna see I have my summation X squared, right? Summation X squared. Go down, you're gonna see my summation Y squared, and also I have my summation XY. So I want you guys plug in those numbers onto your formula here. You could see this. Okay, double check summation XY. That'll be 1021. That'll be 102.148. Summation Y 54.14. Be careful for this one. This is summation X and then square. So summation X is gonna be 8.75 and then you're gonna take square. This is a summation X square. So you already have the summation X square here, 19.563. Okay, now I will use the calculator to calculate this guy. So what we're gonna do, first, I want you guys put the frequency on the top here. Big frequency on the top, big frequency on the bottom. So I'm gonna do frequency 5 times 102.148 minus 8.75 times 54.14. cos parenthesis. Put the big parenthesis on your numerator here. And then divided by another parenthesis. Do the square root 5 times 19.563 minus 8.75 square. Okay, you could see I'm gonna stop here. So I want to exit my square root. And then now I will have a second square root here. And I have a 5 times 601.928 minus 54.14 square. And then get out of another square root, cos parenthesis. Okay, so one big parenthesis on the denominator, and then enter. So you could see 0.906, which is going to be matched from our part A here. Okay, you should get exactly the same answer from part A. Again, you need to know how to find your R using the calculator and the formula, both of the method. Okay, D, is the linear correlation positive or negative, weak or strong? So first, my R 0.906 is really close to positive 1, right? So we know this is a strong linear correlation. And also, this is going up. This is increasing, right? So we know this is going to be the positive slope. Or you could look at here. This is a positive number. So I know there is a strong positive linear correlation. Okay, example 2. I want you guys try to do it by yourself. Use the calculator, find the R, and then use the formula to find the R. And make sure you construct the scatter plot also. Okay, check your work. R equal to 0.809. Again, you're gonna plug in your X on your L1, Y will be on your L2. Your scatter plot should be like this. Find out the summation X, summation Y, plug into the formula. You should find the same answer just like your calculator, 0.809. So again, this is positive, right? And really close to the 1. So that is a strong positive linear correlation. Okay, so this is the first part. You guys know how to use your calculator to find the R, construct the scatter plot, and you know what is the properties for the correlation coefficient R. Second part, we're gonna work on formal hypothesis testing, just like the chapter 8 and the chapter 9. Requirement. It has to be simple random sample. Visual examination of the scatter plot must confirm that the points approximate a strychnine pattern. So before you work on the hypothesis testing, you want to look at the picture. They do have the strychnine pattern. Number 3, outliers must be removed if they are known to be errors. This is the same requirement before you guys finding the R. Notation. N represent number of pairs of the sample data. The R, sample linear correlation coefficient. The rho, population linear correlation coefficient. And we will be using the same X step just like chapter 8 and chapter 9. Look at the original claim. We have the rho equal or not equal to 0. Why we only have these two choices? Let me explain it with this part. Okay, for the null hypothesis, rho equal to 0, alternate hypothesis, rho not equal to 0. or the null hypothesis, less than or equal to, alternate hypothesis, strictly greater than. Same idea for this guy, right? This is the same idea just like the chapter 9. And when you guys working for not equal to, this means to tell. Okay, let me explain this guy again. Rho equal to 0. This is the same idea. R equal to 0. Remember when R equal to 0, we say there is a non-linear correlation. If R not equal to 0, that means there is a linear correlation. And for this one, when your R greater than 0, means there is a positive linear correlation. When your R strictly less than the 0 means there is a negative linear correlation. However, for my class, we don't cover like this too. Okay, we don't want to show if there is a positive or negative linear correlation. We just want to find out if there is a linear correlation. So for this class, we only focus on this one. R equal to 0 or R not equal to 0. And one more time, equal to 0, there's a no linear correlation. Not equal to 0, that is a linear correlation. So that's why my original claim either one of them. Okay, compute the test statistic. So you could see we are using the T. That would be the T distribution. And then the R here, this is the linear correlation coefficient R. So for the number 1 extract information, you want to find out the N and R only. Okay, distribution. So we always have a two-tail example for this class. And the T distribution, it looks like the normal distribution with two tails. After we find the test statistic from the step 4, we're going to write it down here. We want to find the p-value. P-value will be equal to the area of the two tails. So how can we find your p-value? This is the T distribution, right? So we're going to use the TCDF, lower, upper. And then for this session, the degree of freedom, you do have an n-2. You could think about it. For each order pair, we do have a two data, x and y. So that's what the degree of freedom is going to be n-2. Okay, keep in mind, chapter 8, chapter 9, for the student T distribution, we always have the degree of freedom n-1. But for the chapter 10, we will have the degree of freedom n-2. And then I'm going to multiply by 2 because I have two tails. And conclusion here, compare with your significance level. Final works, same conclusion from the session 8.1. Okay, now let's try the first example. Conduct a formal hypothesis test of the claim of linear correlation between the cost of the pizza and the subway fare. So I have the cost of the pizza and also the subway fare. Number 1, extract information. Find out the N and R. So we have 1, 2, 3, 4, 5, 6. So my N is going to be equal to 6. And this time I want you guys use the formula. Okay, use the formula. So try to do it by yourself. Use the calculator, find out the summation x, summation y, plug into the formula, figure out what is your R equal to. Okay, check your work. You should get R equal to 0.98781. Okay, original claim. So with the claim statement here, test of the claim of linear correlation. I want to show there is a linear correlation. When there is a linear correlation between these two variables, means the rho cannot be equal to 0, right? Okay, the null hypothesis and alternate hypothesis. It's always to tell in here, right? Okay, find the test statistic. Use this formula. We're gonna plug it in. Use your calculator. You should get 12.692. Okay, distribution. We have the normal distribution with two tails. The test statistic, p-value will be equal to the area of two tails. Okay, how can we find the p-value? We will use the TCDF, right? TCDF, lower value, upper value, and then degree of freedom. Okay, remember the degree of freedom will be n minus 2, which is going to be equal to 4. You should get 2.22 times 10 to the power of negative 4. Make sure you look at your calculator. You should get 2.22 and then the e negative 4. This is the scientific notation, right? So we want to convert it to the standard form, which is going to be 0.0002. Okay, now we're going to compare your p-value with your significance level. It should be less than or equal to, right? Then we're going to reject the null hypothesis. So think about it, which conclusion is going to be. Your original claim go to the alternate hypothesis, so either number 3 or number 4. And now we have a reject, so that will be number 3 conclusion. There is sufficient evidence to support the claim of linear correlation between the cost of the pizza and the subway fare. Okay, next example. Want you guys try to do it by yourself for the step 1, step 2, and step 3. And these questions will be using the critical value method. And you can see for the number 1 here. I want you guys use the calculator to find your R. So your N should be equal to 5. And your R equal to negative 0.95896. Okay, original claim. So there is a linear correlation. We want to test the claim there is a linear correlation. So means the rho not equal to 0. Then your null and alternate hypothesis with two tails. Okay, distribution. We have normal distribution with two tails. And this is the critical value method. So the area of the two tails will be equal to your significance level, which is going to be 0.05. Now, I want you guys find the critical values. So we have the two tail, you're going to divide it by 2. So the area of the left tail, that's equal to 0.025. So inverse t, 0.025, degree of freedom is going to be n minus 2. Okay, how many critical values do we have? We have two tails, right? So that will be plus minus. Okay, after you get the critical values, write it down here. Now, find the test statistic. Plug it in. You should get negative 5.858. So this is going to be the test statistic. Make sure you will show me where is your test statistic located? So it should be somewhere like here, right? So draw the conclusion. Give me the reason. Your test statistic is in the critical region. So we have a reject the null hypothesis. So that will be the number 3 conclusion again. So this is how you guys do the hypothesis testing using the critical value method. That's it for the session 10.1.